My name's Adam. I'm leading the R&D and open source efforts at SoftwareMill, which is part of Virtus Lab group. If you'd like to find out more about our companies, we have stands outside. I would like to show the progress that we've made trying to make direct style Scala a reality and something that you can use in production. So there will be a couple of demos. I'm sure half of them won't work, so bear with me. There will be also some code. So before we start, I guess I would like to make a kind of a disclaimer. While this focuses on direct style, the premise of a lot of our open source projects that we have in Scala, such as HTTP client, Tapir, and so on, remains the same. So we always supported the entire Scala ecosystem. We always supported a number of different Scala stacks. So, be it futures, functional effects, direct style, Scala.js, Scala native. So this remains in effect, and we still do that. In fact, a large portion of our open source time is devoted to maintaining integrations with all those different effect systems, futures, and so on, which is not that easy. So we support and we will support the entire Scala ecosystem. But that said, I guess throughout last year, we kind of focused a bit more on direct style. And that's for a simple reason. I think direct style complements the Scala offering when it comes to backend development, when it comes to modeling complex business domains, to transforming data pipelines, and so on and so on. We have some great solutions like Cat's Effect, like Zio, like Pecco, and so on. But I think direct style completes Scala offering here, hence our work in that area. So just to maybe bring a bit closer what direct style actually is, I would like to offer you two definitions. So the first one is that direct style is an approach and style of programming where the results of an effectful computations are available directly, so hence the name as well. So you don't get a wrapper around the results of your computations, such as an I/O of future or task. The other definition comes from Martin's last year talk, is that direct style is the opposite of continuation passing style and the control monad. So we will see how this looks in practice. Direct style brings a couple of benefits, such as no overhead when it comes to syntax. So we can use plain old Scala syntax without any additions. We get meaningful stack traces. We can use built-in control flow constructs. There's also a number of costs, of course. You don't get the entire feature set, and you don't get that much safety as you do with Cat's Effect or Zio, but that would be a separate talk, so I won't dive into that here. So what I would like to show is a working example of an application written in direct style. So these components, so all of these are rather, you can say, simple and maybe boring, because these are the things that you would like to have out of the box. And that is exactly our aim, to provide you with a boring toolkit of things that should just work to write an application in a given style. So maybe each of those isn't very complex. Making them work together is a bit more work. So as the base language, of course, we are using Scala. For dependency injection, you can just use plain Scala as well, just invoke constructors. We are going to use Macquarie to make this task a bit easier and tidier. On the HTTP stack, we are using Tapir with a Netty server and JSONiter for JSON. For database, we use Magnum and Flyway. We will see exactly what it is. For concurrency and general direct style toolkit, we use Aux. And for observability, we'll use Logback and OpenTelemetry. So that's like a very high-level view. The majority of the talk will be simply a demo of the application, and we will take a look at how to develop a simple demo is created using the Budzuka template. Budzuka is a template of a microservice that you can clone and explore on your own. So it consists of two parts. So there's a backend and a frontend. So I will the backend start script simply starts SBT in a mode that watches the sources for modifications. So I'll start the backend. There's a separate build for UI. The UI is written using TypeScript and React. There's also a script which watches any source changes, so you can get a pretty nice live development experience. So here we've got the front end started, the backend is starting. The base application that you get is just a very simple application where you can register, this sends a welcome email, you can log in, reset your password. Once again, quite boring functionality, so nothing very special, but a good starting point if you want to see how you can actually develop a functionality, what are the components involved, and how to wire everything together. Okay, so the feature that we are going to add to this application is a new page where you will be able to plan a trip because vacations are coming up. So we will randomize for you a trip, like a trip suggestion to one of Europe's capitals using a random mode of transport. So of course, this sounds very simple. We will make it artificially complicated just for the demo. So to start with the code, so there's a couple of components that we have to develop. So first of all, we have the database side. So in the database, we will store two things. So here's the schema. The schema, as I said, is maintained and applied. The migrations are applied using Flyway. It's a well-known Java library. So first of all, we will have a cities dictionary table where we will store the potential destinations. So I think these are the EU capitals. Not sure if they are all of them, but probably most. And we will also store an audit log of all the trips that we have generated for our users. So as you can see here, you just use SQL. Quite simple. So then we of course want to somehow use this data and store and generate the trips and store them in a database. So that's where the travel service comes in. So that's the place where you actually implement the business logic. So here below we have our model. So this city and trip case classes, they correspond to the tables that you have seen. As I said, we are going to use Magnum to map to database tables. Magnum is a relatively new Scala 3 only database library, but it uses Scala 3 features very nicely, and it's, I guess, strikes the right balance between abstraction and simplicity and being close to SQL. So it uses annotations to define the mapping between names of case classes and in SQL. These annotations, unlike in JPA, for example, they are not used at runtime. They are only used at compile time by a macro to generate a repository. So yeah, here we've got a simple mapping of a city case class to cities. So now the repositories themselves are generated over here. So the repo over here comes from Magnum. What it does is it inspects the city. So as Daniel showed in the previous talk, that's a very good example of a macro. So it generates a repository with all the basic stuff, find by ID, find all, insert, and so on. Again, all the boring stuff is just auto-generated in a quite a simple invocation. Okay, so we are now going to implement our next trip method. So this is designed to randomize a new trip and persist it in the database. So first of all, we need to look up all the cities that we want. So here we just call the findAll method, and we are basically done. An important detail, of course, is that we need to be inside a database transaction. And this is expressed using a capability over here. So this findAll method will only run when this dbtx value is in scope. This, first of all, encourages a structured approach to programming, right? Because this has to be like syntactically in scope. It also is quite light on the syntax, so you don't need, to manually propagate the transaction. And finally, it makes the fact that a transaction has to run kind of explicit, right? Because you do need to have this parameter over here if you want a method to use transactional capabilities. And I think it's a good thing to have, to actually know that a method needs to be run within a transaction, because it impacts how your data behaves in terms of integrity and so on. Okay, so we find the cities. Now we will complicate our lives a bit, right? We could have just called random on the city, but we will actually call an external service to do the randomization for us, just so that we can see some more stuff. So we will actually call 2 external services. So here we are creating 2 request descriptions using HTTP. So the first one will call a service on port 8070, passing in all the possibilities as a JSON array. And the second one will just try to pick at random travel mode. We can go to the implementation of those services. So let's take a look at the pick random service over here. So that's the endpoint definition that we are calling from the other service. It's using Tapir, right? So here we have the path. We are expecting a JSON array as input. And what we do as part of handling the request, we just pretend to do some work, of course, and then we return a random element. We then bind this endpoint over here to point 8070, and that's basically the whole application. So we will actually need it to be running. So we run it. So there's some logging setup. And we also need the other application running as well. So the demo will actually work. OK, so we've got this running. So once again, I guess this is all quite simple. Here, the business logic is expressed using direct style, right? So no effects, no wrappers, just simple code. OK, so now we can go back to our travel service. We can close that and close that. So we've got these 2 requests described. We still have to run them. So they are independent, so we will run them in parallel. So to run them in parallel, we will use a method from Ox called par. Par simply runs 2 blocks of code in parallel. It takes care of all the error handling. So if any of these fails, the other one will be properly interrupted. So there won't be left any garbage, like any threads won't be left behind. And yeah, so here we are calling these 2 with a send and obtaining the body. And finally, we create the trip that we want to return to the user, right? We have obtained the destination city and the travel mode. So the last thing that we have to do is we have to insert the generated trip into our audit log. So that we are doing that here with the trips repo.insert. So that's simply a function generated on the repository. We are using the tap inline function that's from Ox as well. I think it's actually quite popular in Kotlin to use functions like pipe and tap. They have a different name, which I forgot, but they do the same thing. So the tap and pipe are actually very useful, and they often save you from doing, assigning a val manual and so on and so on. And since this is just, an inline method, it doesn't have any cost. Same with pipe. So it's actually a very small but a very useful thing. OK, so we've got our trip inserted, and we're almost done with the service. So one nice thing about, I think one more thing that I would like to talk about is how we inject dependencies over here. So this service has a couple of dependencies. As you can see, there's a backend with which we try to send requests and an ID generator. And I have no idea why this is red. Anyway. So these 2 dependencies are expressed using a constructor. As I said, we are using Macquire for generating the final, for assembling the final service graph, meaning that we don't really need anywhere to explicitly call new travel service with the parameters. We just need to say, create an object graph where this travel service is some further dependency. We will see exactly how this looks like. But when it comes to development, what is nice is that when we add a new dependency, we don't really have to propagate changes anywhere further. So for example, if we add a new clock dependency over here to use it, so we just add a constructor parameter, and we will use, instead of using instant.now, we will just use a clock.now. This might be a good idea for testing if you want to control the flow of time. We save things. So that's the only change we did. And if we now go to our terminal where this is constantly recompiled, you can see that things recompiled just fine and restarted, right? So the macro that generates the object graph in the main method actually supplied this additional parameter over here without any problems. Okay. Then we have, on top of this, we have the API layer. So the API layer is, once again, just tap your endpoints. You can see, first of all, we have the description of the travel endpoint over here, the travel/next. Then we have the thing that the shape of the JSON that we return to the user. And we have the implementation of our service, where we simply call travel service.next trip. And one detail over here, we call it in a transaction. So this db.transact actually provides a dbtx implicit value, which is then passed implicitly over here, meaning that this invocation is done within a transaction. And this API is then exposed to the user. So we can actually go over here to the API documentation, and we have our endpoint over here, because documentation is automatically generated for all endpoints with Tapir. So we can try it out, we can execute, and hopefully, yeah. So the next travel suggestions that we get is from Warsaw to Oslo by bus, or maybe you would prefer to go from Warsaw to Amsterdam by bike, which is not a bad idea. Bike is useful in Amsterdam. So this works nicely. We can also add a detail here. For example, we've had a description, your next trip. So this should be recompiled and eventually show up in the documentation. Yeah, so this is up. And yeah, you'll get the description over here. So this is really live, if you didn't believe me before. Okay, so now going up this stack, where's IntelliJ? Going up this stack, where this is all wired up using Macwire. So at some point, we get to the main class where we actually have to create the object graph and to wire everything together. So that's where the dependencies class comes in. The dependencies class gathers the top-level dependencies that are needed to run the application. So that's a case class that you have to define. And then over here, we have an autowire dependencies call. The way autowire works is it will use the default constructor when a dependency is needed. If a travel service is needed for the travel API, it will just call the default constructor with parameters that are defined, that are looked up recursively, unless there's a specific instance or a specific factory method given as parameters over here, right? So, for example, we are saying that whenever our service or our API class needs an instance of an HTTP backend, use this instance. Same with OpenTelemetry and so on and so on. So you typically provide, some infrastructure instances or infrastructure factories as explicit parameters to the autowire. Everything else is automatically generated. And in the end, we have the main method, which is the entry point to our application, in which we start the HTTP API, which simply binds the socket and exposes all the endpoints. Okay, the nice thing here is that the direct style approach nicely integrates with the entire Java ecosystem. So we are running on JVM 21 because we are running on virtual threads. And we can, if some functionality is missing, we can always fall back to Java. For example, when it comes to observability, we can integrate with OpenTelemetry very easily. By default, OpenTelemetry in Java uses thread locals to pass the context. And here it just works. We don't really need to do much. The only thing that we need to do to integrate with OpenTelemetry fully is to add some interceptors for Tapir. So for example, if you have the service over here, so we need to add this tracing interceptor so that any context information that's passed via headers is actually propagated. So it's read from the headers and set in memory. Same for the HTTP backend. It needs to be wrapped with an OpenTelemetry wrapper so that when a request is outgoing, the current trace ID is set in the headers. And we can see how this works if we try to generate a couple of trips. Try it out, execute. Okay, Warsaw, Lisbon by train. That might be challenging. If we go to the logs over here, you can see that here's the trace ID. It's 00B9, right, for our request. And the same trace ID is used in the other services. So this is all nicely propagated into the other services. We can also go to Grafana and actually, there's some trace ID and explore the traces. You can see that here's the complete call graph of our services, right? So we've got our main endpoint, the API travel next endpoint, which then sends a request to the pick random service and to the travel model service. These are done in parallel, right? So the traces are in parallel, and they take some, artificial amount of time, right, to complete. So this all nicely works without really much effort. So there's like 3 integration points that you actually need to set: the Tapir interceptor, the HTTP backend, and one more over here to one more thread factory so that the traces actually propagate when you create child virtual threads. The last thing that I would like to show, so these are like the total basics, I guess. We've got the database, the HTTP. One more thing that I'd like to show is streaming data. So very often in applications, we have to stream some data. Here we will show you. Here I will show you how to do it using Kafka. So I will actually start this additional service so that it starts in the background. But here we are. So here we have a background service whose task is to continuously monitor any new trips that have been generated and that are inserted into the database audit log and write them to Kafka. So to implement this streaming, we are going to use an aux feature called flow. So if you know FS2, if you know Akka streams, it's a very similar feature, but adapted to work with direct style. It also interfaces with reactive streams if that's what you need. So what we do in the service over here, we have the start method. So the start method needs to be run within a concurrency context. So that's once again an aux capability that's used to express the fact that you need to be within some context. And this capability gives you the possibility to fork computations in the background. So the only thing that the start method does is it forks computations in the background. It forks a new thread which calls run. This run will be, if it runs forever, it will be interrupted when this scope ends, so when the whole application ends as well. So in the background set, what we are doing is we are going to create a flow. A flow is a lazily evaluated stream, a lazily evaluated effectful stream that can do anything, which has a very similar API to FS2 or Pecco streams. So what we are going to do here is we are going to create a flow which emits a value every second. And then it does a map stateful. So that's the last last time that we have actually transferred data from the database to Kafka. And on each tick, what we are going to do, we are going to select all the new trips. So here we are using a feature of Magnum, which helps you in writing SQL queries. So we are once again auto-generating table information using the same trip class as before, using the table info macro, and then we can use things like .all, which is just all fields, or we can just reference the fields over here. So we are selecting all trips that have been created since this last timestamp. Then yeah, we are returning the new timestamp from which we want to run the next query and the trips. And then over here, what we do is we map this a couple of times to create some Kafka records, which we will publish on Kafka. And finally, we run this whole flow. So this flow is lazily evaluated. So creating the flow doesn't do anything. The flow has to be run. So we create a Kafka drain, which will actually run the flow and publish all of this data to Kafka. Hopefully, we can see that it works. So yeah, we've got, you can see the Kafka logs. If you work with Kafka, you probably know this. So we have a Kafka consumer started. And now we can actually try to create a couple of trips. OK. Warsaw Athens bus. Awesome. So topics, trips, messages. And now we have to produce some. OK. Yeah, and they show up here, so this even works. That's surprising. OK. The last thing, I don't have much time, but the last thing I wanted to show you is how this all integrates with front-end development. The way Budzuka is set up is that whenever there's any change in backend code, it's of course recompiled and restarted, but also an OpenAPI file is generated basing on the description of your endpoints. There's like a separate main file which gathers all these endpoints which are available as fields on objects. And generates this OpenAPI file. And then the UI build, what it does, maybe it will be visible over here. What the UI build does, OK, it's not visible. Anyway, what the UI build does is it auto-generates TypeScript stubs so that you, well, not stubs, it auto-generates TypeScript code, which allows you to call the services, right? So if we now create a React page, where we can actually generate these trips, we can use this auto-generated use post-travel next method, which will accept and return all the types that are described in OpenAPI, so we don't have to write this by hand. You can see that I've added this description to the endpoint, and it's already automatically generated over here in the code as a comment. And just to show you that it works, we can go to the /trip over here. And yeah, so this calls our backend through the auto-generated TypeScript code. So the point of the main source of truth is the tap your endpoint definitions, from which the OpenAPI YAML is generated, from which the TypeScript services are generated in turn. OK, so that's it for the demo. 1 minute and 30. OK, we'll make it. So yeah, there's, I guess, a couple of direct style Scala principles that emerge. First of all, we are not using any reflection, of course, which also makes it possible to use GraalVM native quite easily. Instead, we are using compile time generation from metadata. We are using implicit self capabilities. So we've seen that with Ox. We've seen that with dbtx. The context functions such as supervised or as db.transact provide these capabilities and allow you to eliminate them from function calls. When it comes to using resources or when it comes to concurrency, we are taking a structured approach. So the syntactical structure of the code determines the lifetime of various things, right? In terms of the aux scopes, it determines the lifetime of threads. In terms of transactions, of DB transact, it determines the lifetime of transactions. So the way you write your code corresponds to how long things last. So we are not entirely done yet. We still have a couple of things to do. Probably it will be a never-ending story. So we would like to finally release HTTP Client 4 and a bit later aux 1.0. So these things are no longer on a milestone, on an experimental version. There's some integration between aux streams and Tapir left to do. The Buzuka template also needs some polishing, and there's a couple of features missing in the synchronous native server. So if you would like to get involved in open source and Scala open source, I think that's a very good starting point as well. So there's a number of issues that you can pick up, and you're of course welcome to. If you'd like to start with direct start Scala and Scala in general, we've got part of our work last year was working on documentation. So, for example, we've got a number of examples, both for Tapir and for HTTP, which are nicely categorized for different use cases, because I guess it's easiest very often to just take a look at the code, how things work. This list is not complete, so I've got like 10 more left to do, at least, from the ones I know, and a large number of examples that I don't know yet about. So I guess that's a good starting point to actually learn how Tapir HTTP works, how to expose a server, and so on. Plus, there's a number of Tapir videos that we've recorded, which, if you prefer this way of absorbing knowledge. And I guess that's all I had. Currently, this application, the stack that I've shown, works with Java 21 only. I guess we have the basics covered, so the HTTP DB layer streaming is there. Some more integrations would be nice, and I hope these are coming up. Also good areas if you'd like to contribute. If you like the projects, take a look at GitHub, leave a star. And yes, that's all I had. Thank you.